is this there's a kind of a local category which lives on the category in the uniform run space. And there's a global category, which is just a category. And there was the notion of a unital and a lax unital. Unital local to global functor. Which involved the following things. So at every point, well, just informally, at every point, I have the functor sub x, which maps the local category to sub x to the global category. And for x included in x prime, x maybe is a point in the ground space, that's underlined. X is included in the x prime. Well, for the local thing, there's the unit structure. So there's a unit insertion functor to x prime, and then each of those are supposed to map the global category. And so the nominal lax unital is the data commutativity for all of these, and the lax unital is where it commutes only up to where it only commutes up to a natural transformation of segments. So anyway, and so the point is that you can formally, from one of these, you can formally produce one where this arrow becomes an isomer. And there was this well, via this funny formula. Yeah, I don't know. I think that's all that I wanted to re-say more slowly. So there was a question, yeah.
Yeah, I'm thinking about something about like gravity, like some weaker notion of like offer, and this is why there's like
Yes. The technical term is pseudo-proper.
Okay, so does this allow actually something?
Yes.
And is this saying something like
roughly it's saying that it can be expressed as a kind of colimit of proper varieties.
and you're using this for P small?
I'm using this for sure, but I mean for any it's a property of the space rather than it implies that like any map between pseudo-proper pre-stacks, there will be a kind of an adjoint.
Oh, that's we're not saying it's like P small, like this more.
It's not a property of P small. It's a property of the Ron space.
Okay.
So there's a general statement that if you have a map between pseudo-proper stacks, then the pullback functor has a left added.
Okay, I was very confused because like in P small,
Yeah.
for example, like the fiber over a point with like only consists of like
It's like a pointed version of the Ron space.
they will only consist of subsets that contain that.
Oh, that sure, yeah.
Then like that feels something like a puncture, like you would have some like puncture curve, okay, but like puncture
Every tool is on points.
like a subset containing x is the same as like a subset of like x minus n.
No, because no, the topology theory is different. So this pointed version of you're asking what is this pointed version of the Ron space, right? Or I guess what's a formula?
Need more. A1.
I think for
Point,
one
not
it's
point.
closed in the run.
You see the point is like the way Indeed, a point is, that's a closed subset of the Run space. If you like. I mean, the way you can think of it, like, why is it not just some kind of configuration of points on the complement? Is because the way the Run space is built up, it's like you look at kind of arbitrary points and you look at it up to the equivalence relation, that if something is doubled, then you can ignore it. And so what you're allowed to do is double the point that you already have in this kind of polling verification. That's why it's not something just about but anyway, that's also
So maybe as a first approximation, it's not like the function version of x, it's one point compactification of this function version. You're still,
yeah.
you can still go off to infinity.
Yeah. And the point there is just that point and nothing else, for instance. Yeah, I think I won't be able to do this at the board now, but a good exercise is to, so I wrote Ron is this column. They are over non-empty finite sets and surjections. Non-empty. Opposite. Is to write down a similar formula for when I fix a point. Which also is going to be a formula of this flavor. Where obviously each term is going to be a proper variety. Let me close that as an exercise. Trying to do it in front of the board. Yeah, maybe let me try to answer Sergey's question from before lunch. Which is he asked, the question is, well, I said this has a left adjoint. What is that? So in particular, there's supposed to be a map from an original functor to this one. What is it? Let me maybe answer this question, which is that in this Z, remember what this is. So this is all. This is like for a Z point of the Run space. This is everything in the Run space that contains that generalized point. That's what the space is. Let's see. That's this symbol. And so the point is there's a diagonal map. Which just picks out the point itself. I hope it's clear. I mean, because there's a map from Ron to Ron inclusion, which is just where the two points are the same, are equal. And so this induces a map like this. And so in this in the diagram here, let me rewrite it. In this diagram here, one could instead, at this point, pull back along the diagonal. Well, so there's a kind of an adjunction. These modules. See. Diagonal. There is an adjunction like this. Oh, great. Answering your question. So, let me repeat why this composite receives the map from the original function. So, saying that there's in this funny space of subsets that contain a given generalized subset, you can look at just that one. That's equal, so that gives something diagonal. So there's an adjunction like this. And the point is that if you go to here and then to here, that's the same as the original function. Is the assertion. Yeah, this. Oh, wow. This as drawn commutes. Sorry. So you can just apply your functor, or you can insert unit. And then
What's happening?
no, I'm getting my. It's fine.
You check.
So the point is this composite is just F. This is the. Because restricting along the diagonal, because insert unit, because well, this factors through.
Nick, why don't you, before you apply last function, just if you write it as a composite, before you apply piece small lower sheet, insert diagonal upper sheet, diagonal lower sheet.
Yeah, that's what I'm doing.
Yeah, because if you write the formula, it will be clearer.
No, sorry, I'm justifying what. So it's clear that there's a map like this. Sorry, I'm answering a different question, I guess. I'm addressing the question of why doing what you said produces the original function.
Yeah. Yeah, and it's, yeah.
And it's well because there's a diagonal upper streak here. Similarly. And I guess this commutes. So if you insert unit and then you restrict by the diagonal, that's doing nothing at all. I hope that's clear because insert unit, like on the original space did nothing, and then it just told you what to do for more points. And so because you have a commutativity of this, that means that that means that this composite is the original F, but this composite is the same as you can use the adjunction. There's a left adjoint to diag upper shriek, which is diag lower shriek. And so well you can, instead of doing this composite in the middle, you can insert the unit of this adjunction. That gives the map from F and this unit. Okay, other questions?
I think it's 2 p.m. I think we should stop.
All right.